Welcome you all to this cryo-EM course. Last class we discussed little bit about the CTF estimate, and CTF estimate. When we are doing that, mostly we are discussing about that three dimensional how the contrast is transferred and how it is recording in the images. That time I discussed couple of times about the envelope function. That is important to know what is that envelope function. So, I hope you remember that we discussed about the different kind of aberration. So, there are four major aberrations we discussed. The first aberration I told chromatic aberration, and then second one I told astigmatism, and then spherical aberration, and other one that coma. So, spherical aberration we cannot correct the spherical aberration, we can reduce the spherical aberration. The chromatic aberration will be there because chromatic aberration is connected with our energy of the electron. So, if you just remember that how this chromatic aberration it is happening, if there is a two different types of electron and it has a different energy, some electron it will converge here and some electron it will converge here. So, if you just consider that okay, I have an object like this one and I want to image this particular object, and then one it will form one image here, and because here you have a different kind of energy of that electron, the electron does not have the same energy. So, if you just consider one has E and another one is E plus delta E, and then if we have a same magnetic strength here, it will converge in a two different plane. One it will converge in one particular plane and the other one will converge in a other particular plane, because we need more energy. If we just consider this is my stronger energy. So, you need a more stronger field if you want to converge here. So, when they are merging in a two different plane, so same particular image, one image it will form here, another image it will form here, but we cannot see two different image, we will just get an average image of both of them. So, one image is forming here, one image is forming here, and that will give us an average image. So, average image how it will look like? So, average image will look like this. So, now in this you can see overall shape there is no change, right? It is again that top is circle, bottom is circle, but what will happen when they are aligning if we just split them into a wave? So, if the low frequency wave, if we just consider this is a low frequency wave and this is also a low frequency wave, they will come together. So, if you look at these two wave, blue and red wave, and the low frequency signal, if you just consider, there is not too much change between them, even their position also, even they just replaced. But if we go further, if we just go more and more, that okay, if you just consider this particular object is made by three different waves, or if you just consider that okay, I have one wave is like that, there is a this kind of object and I want to image it. So, this wave is particularly made by three different wave. So, first wave is this one, there is no change. Now, look at the second wave. The second wave, probably this is the second wave, it is coming, this is going down, again it is going up and going down like that. Now, if you consider the second wave, if I just try to draw that one also, there is a shift. Now, you can see in this low frequency signal there is not too much change, but the high frequency signal, even if we start high frequency signal, you can see those waves are completely opposite with each other. So, they are basically almost cancelling each other. So, if you just consider this particular area, this particular box, they are cancelling each other. Here also they are almost cancelling each other. So, what is cancelling? Basically they are cancelling the amplitude. The amplitude is reduced, amplitude is going down. So, now if we want to plot this one, if you have a CTF, what is going to happen? Initially low frequency there is no problem, right? But when you will go more and more high frequency they are going to reduce. Okay. So, there is a two types of coherence, that is spatial coherence and temporal coherence. This two coherence is contributing lot in the high frequency signal. So, one is this one, another one we can consider. If electron is coming in a different angle, one is coming here, one is coming this direction, they are not very coherent from the beginning or after interacting, if they are not. So, if you just record them, again similar kind of problem can happen. So, if you just consider this image we are trying to record. So, this red one perfectly it will record, then blue one it is recording somewhere here. So, the blue one will be a little bit shifted. So, now if you look this one, so if you try to merge them together, what you can get? You can get an average image, so something like that. So, you can see the problem it is coming in this particular zone. The overall this low frequency, this is coming very nice. So, if you want to plot it again this is going to come like that. If there is a low frequency signal, that low frequency signal is almost merging together and that is giving a average amplitude kind of thing. But when there is a high frequency signal, if we just try to plot them again, so again there is a problem in the high frequency signal. You can see they are cancelling each other in this particular case. So, if you just consider this kind of problem when you are collecting the data, that okay, there is a temporal coherence, there is a spatial coherence, and because of the environmental effect it is high frequency signal, it will be always less. So, if you go back to your previous classes where I was talking about the diffraction pattern, and if you look at your diffraction pattern, what you can see, again I am talking the same thing, the central part it will be very dense white object, white. So, all this low frequency signal and all this complete amplitude is transferred. Now, if you go all this diffraction pattern, you can see it all over, it is spreaded all over the square. Now, if you go very far from the center at the edge, that high frequency signal, those are the high frequency signal you are trying to record those. So, if you look at this high frequency signal, their intensity is also very less, very less than what do you have in this region. Why? If everything is transferred properly, it should transfer. So, one thing is that when they are scattered with multiple wave, they are so when the waves are going, if there is a central, so you are getting, and then you will get more scattered electron like that. So, when there is a scattering, there are multiple waves are cancelling each other. That is one of the reason that intensity will be very less when you are recording those intensity. How they are cancelling each other, we cannot cover in this course, but you just remember, or if you just go to BSc Physics and study this, you can find out that okay, so at the central you will get a very bright spot, and if you go from far away from the center, so first maxima, second maxima, third maxima, so many waves they are scattering with each other, and many waves they are cancelling each other's intensity. Only very small amount intensity is going to stored in the first maxima, second maxima, third maxima, like that. So, that is one of the reason that intensity it is getting low, how they are cancelling each other, that we already discussed. And not only that, that different types of energy, different types of angle when electrons are coming together, what is affecting? It is affecting the high frequency signal. So, low frequency signal it will go like that, and then signal it will go like that. So, now here when intensity is very low, so and there is a lot of noise is there, after a certain point this high frequency signal will be almost equivalent with your noise. So, you cannot figure it out which one is the noise and which one is the signal. So, you can see there is a damping effect of that signal, and that is called the envelope function. So, this is called envelope. So this is called, I'll just write it, envelope function. So this is our envelope function, and that we are going to record it. So always remember that when you have the best microscope, when you have a very low defocus, signal will all go all the way and you can read all this signal until Nyquist. Here, you know, this because of this envelope function we are losing lot of high frequency signal. Now if you are using a very strong defocus value, what will happen? The signal will cluster only one particular point and many signal will be lost in somewhere. So that is the direct relationship between the different defocus value and signal transfer, and what is the relationship of the envelope function also. So now we will go to the directly the pipeline, and I'll show you how to use those pipelines. This is basically of the CTF transfer and signal transfer. I'll show you couple of images also that will help you to understand what is that CTF correction. So always remember that when we are talking about that, if we are considering this is amplitude and this is our frequency, spatial frequency. So when you are talking about the CTF, some signal it is coming in the negative. So most of the time we have to flip it back. So that is called the phase flip. We'll flip that phase back and we'll erase this particular portion, this one. So we have a proper wave like this one. So that is called the phase flip. Okay. So one more thing you should remember, that when we will collect data, we collect data in a different defocus value. Why we collect data in a different defocus value? If you look at here, what I told, this is our contrast transfer function, right? So I am just drawing it like that. So this is my contrast transfer function, envelope function is there. I also told that we have to flip that phase back. So all will be in this particular direction, in plus amplitude direction. So we have to flip that phase back. So this portion it will be erased when you will flip the phase. So now our wave will be like continuous like that. But still there is a problem, some particular point, this 0, we don't have information for this 0, right? We don't have this information for 0. That is one of the reason to satisfy this one. What we have to do, we have to collect data at different defocus value. So generally if you go to the microscope room, you can see people are collecting data from 0.05 micrometer to minus 2.5 micrometer, or sometime minus 1.5 micrometer to 3 micrometer, and so on. What we are doing when we are collecting at a different defocus value, it is not like that one is collected here and one is collected here. It should be 0.5 minus 0.5 minus 0.75, then 1.5, all micrometer, and it will keep going on like that. Now we have this, right? What will happen if we collected a different defocus value? First you consider that this is our first CTF curve. So those things we have to flip it back to this, but still 0 will be 0. Now if we collect a different defocus value, so when you have a second defocus value, okay, then if we have a third defocus value like that. So when we are considering this is 0 for the red one, but you can see for green one there are some values, where the other hand blue one has some values. When this blue one is 0, if you look at this green one has some values, and red one also has some values which will flip back to this side. So even this 0, if we collect a data at a different defocus value or series of defocus value, that will help us to recover these 0 values. In details we can discuss in the later in any other workshop, or if I design a course where we are going to discuss about how the CTF is going to affect and how do we correct, how do we actually do the image processing. That time we will discuss more. At this moment we do not have enough time to discuss in details. You just remember that defocus value, very high defocus value, it is going to affect our signal. We are losing high frequency signal if we high defocus value is not good for our sample. So prefer not to use very high defocus value. So generally 0.5 micrometer, if you can see your sample, just stay within that range. To this range it will be better. Definitely at high defocus value your contrast will increase, you can see particles clearly. That is good for your eye, but that is not good for your recovering the signal. But same time you need some kind of contrast. So someone can argue that okay, I want to collect everything at zero defocus, and that will be the best possible thing, we can do it, and then we are restoring all the signal, we are not going to. But the problem it is that if you have a zero defocus value, your contrast will be so low, you cannot see the sample. That is the reason you need some kind of defocus value to align the particle. In last class I was talking about that one of the limitation, alignment, precision in the alignment of the images. So if you do not have the contrast properly, if you cannot have the signal, even when the computational tool is going to align and going to calculate the cross correlation value, your cross correlation value will be wrong and it will completely misaligned. And if your signal it is very low, if your contrast is very low like that, so it will be almost equivalent to your noise and your computational tool. So the red one is your signal at very low defocus, zero defocus, and your signal, it cannot distinguish your signal or your contrast with your noise. That is the reason you need some kind of defocus value to see the particle, which will help you to align your particle properly. Also remember that whenever you will collect data, you collect data as a series of defocus value, not a single defocus value. When you have the single series of defocus value, that will cover all these missing cones. And always remember, whenever you will check your data, when you have the signal, so what frequency you are getting all these signals. So even if you are getting this signal, if it is ending like that, this is bad. If your signal it is going like all the way towards the end, that tells you what is the maximum resolution you can reach. So you are always expecting as much signal as possible at the high frequency. So if suddenly all the signals are cutting at 10 angstrom here, whatever you do, you cannot reach beyond 10 angstrom. But if your signal it is going all the way down to 3 angstrom or 2 angstrom here, high frequency signal, if you can restore here, that will help us to get a high resolution images and the structures. Let us take a look to the PPT and we will go through the workflow ones that will help us to understand what we are talking about here. Okay, so this is the workflow of our the workflow of that 3D reconstruction what we are talking, right. So this is the basic workflow that we want to do, the typical structure determination for the ReLine process, and the process or we are going to okay. So here it is mentioned that there are some part it is putting the star marks. So if you remember that if movies are not there, so there is no point of the drift correction or motion correction. Again I am reminding you guys that what is movie, when you are collecting a image, we are not collecting a integrated single image, we are collecting a multiple frames movie image, then we are aligning frame 1 with the other frame, second or third or fourth, and then trying to align them in such a way so there will be no drift, and we are correcting that. When we have this correction, that is called the motion code. So whenever we will get the data, first thing, this is called the beam induced motion correction. So this will correct the motion first. So beam induced motion correction. When this beam induced motion correction is done, we will take that integrated image and then we will go to CTF fine tool, or it is called the CTF, the contrast transfer function estimation. So contrast transfer function estimation, basically nothing, it is giving us that option that we can calculate our defocus value and how much signal we are storing or how much contrast we have, that we can calculate from that one. Okay. So that is one important part for our study. So we can discuss those things later in near future. Then we have to go for manual picking. Manual picking is nothing that I already discussed, that when you have an object like that, individual protein molecules at different orientation, you have to make a box. When you will make a box, what it is going to record? It is going to tell that image number, it may be the image 1 or image 2, and then it is going to store that coordinates, that x and y coordinate of this particular individual particles. So first it will read that image number, then it will give you the particle number, that particle 1 x coordinate is that, y coordinate is that, then particle 2 x coordinate is that, y coordinate is that, then again particle 3 x and y coordinate. So same thing it is going to do for all the particles. So that is called the particle picking, where we are keeping x and y coordinates. Then we will go for 2D classification, and then again we will use that 2D classification, that nice 2D averages for picking more and more particles. Initially when I started, I told you that we need 20 lakhs particle or 40 lakhs particle. So 20 lakhs particle, this single protein molecules we cannot pick by hand, it will be very time consuming. So what we are doing, we are taking that small amount particle and then we are calculating a 2D averages. So from this 2D averages we are getting a very nice shape, we are increasing the signal to noise ratio. What is 2D averages, we are going to discuss more in the next class. So when we have the 2D averages where signal to noise ratio is high, we are using those 2D averages. So this 2D averages as a template or reference and go back here and pick more particle as a reference based picking, that is called the auto picking. So we are using these 2D averages where the signals are more, those signals we are using to again pick the particle, and 20 to 40 lakhs particle, that is called the auto picking. That auto picking, that is called our initial data set. Again we perform the same kind 2D classification where we will get a 2D averages, then we will calculate the 3D classification. 3D classification means we have a 3D volume as a reference, and then we will align all these raw particle again and again to calculate the 3D classification, and finally auto refinement and so on. At this moment if I explain those things, this part it will be very difficult for you guys to understand. So just avoid this part, only just remember until this portion where we can get the final 3D structure. If we go to the next slide, now we have to cautious about whenever we are data collecting, there are different kind of power spectrum, you have to look at those power spectrum. So now you are very much familiar that this is one of the best power spectrum, and here you can see this is a elongated power spectrum. Those are highly astigmatic, it may be the objective astigmatism or condenser astigmatism, and this one is a terribly astigmatic, and also the different defocus value, you can see this kind of pattern. So in this particular case, those kinds of images if we are getting, better to reject those images immediately. Now sometime those are the best image, you can get it from here where you can see all the thorn rings. So you can see this is 1, 2, 3, all these thorn rings you can see it, which is giving us a very good idea how our data quality is. We are always expecting a very high number of thorn rings, that will give us more confidence that data collection is perfect and it should be perfectly circled. Here you can see those images, there are some kind of problem in these individual images, that is why power spectrum is not looking as good as that. Whenever you will be in a microscope center or imaging center, it will be better to focus on those images and figure it out. If you are getting this kind of power spectrum, better not to collect data. So just erase all these things, and if you have this kind of power spectrum, it is good and go for a data collection. Here you can see some kind of problem it is there. It is again a power spectrum where you have the signal, so you can count all these Thorn rings one by one, and you have signal somewhere here. So in both the cases signal is somewhere here, but the signal is missing in this site. So there is either a drift or some other problem is there, maybe the alignment is not corrected properly, that is the reason we are losing signal here. When we corrected the same image, you can see this is the perfect Thorn ring, you can see until here. I can easily read Thorn rings here, and this tells you that this is the low frequency area, low frequency signal area is here. If I just split again, and these are the high frequency signal. From this high frequency signal where you are having the Thorn ring, from if you calculate that, you can tell that much resolution you can achieve. So if I can see the rings until here, and if this rings is somewhere 4 angstrom, so we can tell that my data set has a 4 angstrom signal. So there is a high chance if I average more and more particles, maybe I can reach that 4 angstrom structure or below 4 angstrom structure. So we already discussed about the CTF correction and on. Now we will just show you little bit about the so this is how we collect the data, and now I will show you little bit about the how this data looks like. When we have this data, you can see it here that these are the noisy images. Sometime if we just calculate the averages of these noisy images and put more same orientation particle together and calculate the average. So when you are aligning the particles, so what we have to align, if you just consider that we have a huge number of people are sitting here. So first I want to segregate a class, so where who have heights like me and architecture like me, that will make it in one group. So what we are considering, we are considering the height and the overall body shape, we are keeping one group. Then above 6 feet height or 7 feet height, the another category, below 5 feet height another category. So initially we are keeping some very low resolution kind of features to align and segregate the data. Same kind of things we are doing when we are calculating the 2D averages also. So here you can see bunch of noisy images, and then when we are aligning them properly, we are just adding the signal and trying to boost the signal. When you will boost the signal, you can see some kind of features on those particular images. So that is basically called the averaging, that we are averaging the images, we are same orientation particle, we are putting them together and trying to calculate the high resolution features. So here you can see the similar thing, that a very low resolution image here, very low resolution image here, but we are averaging them, which is helping to increase the signal. So this is how we are implementing the 2D classification and averaging techniques. In next section we are definitely going to discuss more about we are going to discuss more about the image alignment part, as well as the 2D class averages. Here I just want to show you one more thing, that the CTF estimate or CTF calculation we are talking about, right. So here you can see there is a blue curve, there is a orange curve. This is in a particular defocus value in the microscope. This is the CTF, that contrast transfer should look like this orange curve. So this is the estimate of this contrast transfer when this is a perfect signal, and you can see all this contrast is transferred appropriately. Now this green one, so if we just consider that green one is our latest one where we collected an image and the signal is transferred, this green one, and you can see after a certain time there is a drop because of the envelope function. It is not reaching in this particular amplitude all the time. So there is a gradually drop of this signal, but this signal transfer is matching with that theoretical one where this one is perfectly matching with this curve. But there is a signal, there is a, due to the amplitude function, this due to this envelope function, this amplitude is reduced drastically. After a certain time, if you go here, all these signals are jumbled up in such a way we cannot distinguish individual peaks, and those are coming within the noise zone. So the signal and noise is almost similar. So we have a cutoff. If you look at this blue curve, here it is telling how much signal we are getting here. So from this called the CTF estimate, and then we are correcting that based on this defocus value, this will change. We will flip the phase which information we are storing in the image, and we are utilizing those things for the image processing. For CTF only this much is enough for now. We can discuss these things in the advanced part. We are not going to discuss at this moment. In the next class we are going to focus on the 2D class averages, calculation, and the 3D reconstruction and so on. Thank you all for your attention.